we're going to look at multiplying special cases, and there's two special cases I want to introduce to you. Still going to be multiplying with polynomials, but if you can recognize these two special cases, it would save you time when solving. So your learning target is still that you can multiply two polynomials. So our first case is called a square of a binomial, and this can be seen two ways. It can be a, which can be any number you can think of, and you add it to another number, and then you square it, or you can see it with the difference, so it would be a minus b squared. And so the first question is, why is this considered a special case? One thing I want you to recognize that when I say a plus b squared, that would be the same thing if we write it out. It'd be like multiplying two binomials, a plus b times a plus b. Again, same thing with a minus b squared, so it'd be a minus b times a minus b. Since they're the same exact term, then that's why we can square them. It's kind of like saying 5 times 5 is the same thing as 5 squared. Well, a plus b times a plus b is the same thing as a plus b squared. So the first thing I'm going to do is explain why this is a special case with the distributive property. So we'll do with the addition one on this problem. Okay, so just as I've recognized or told you before, this is like a plus b times a plus b. Now, if we think about the distributive property, that means I'm going to take this a and I'm going to distribute it to the second binomial. So mathematically, it will look like a times a plus b. And then I'm going to take this second b and I'm going to multiply it times or distribute it to that second binomial. So that would be b times a plus b. Well, mathematically, if we work this out, it would be a times a, which is a squared. And then you would get a times b, which is ab. And over here you get b times a, which I like to write as alphabetical order, ab, and then b times b, which is b squared. And then remember, we've just did this in the last lesson. When you're multiplying two binomials, you can combine those two middle terms. So we end up with a squared plus 2ab's plus b squared. Okay, so if you're going to notice here that this first term is the first term of your binomial squared. The last term of the trinomial, or right here, is the second, or is that last term of the binomial squared. And then this middle term is 2 of the a times b. In other words, 2 of the product of the first and last terms. So that's why it's 2ab. And I'll show you some examples with real numbers. We can also look at it with a visual model. So those of you that like the area model, or known as the table. So if we make this table here, and we put our multiplication symbol here, and then we can put a, we'll do the difference here to see how they mathematically look different. And then we'll go a and then minus b. So mathematically, I'll write it up here. We're doing a minus b squared, which is also the same thing as a minus b times a minus b. Again, this is a special case. It's known as a square of a binomial. It's a square because it's the same term squared and they're binomials. So in this corner, we would get a squared. In this box would be a times negative b, which would be negative ab. In this box would be a times negative b, which is negative ab. And this bottom box, negative b times negative b, would be a positive b squared. So notice again, we get a squared, just like we do above there. If we combine these two middle terms, you have negative ab and a negative ab. That means you have 2 of those. And then you have your b squared again. So the only difference between when we're doing it with a sum versus when we're doing it with a difference is that your middle term, instead of being a positive twice, the product of the first term and the second term, it's a difference. So the a squareds are still exactly the same. The b squareds are still, oops, I forgot my square there, are exactly the same. but this is a positive 2ab and this is a negative 2ab. Okay, let's look at some examples here. And I just wrote, those of you that like it in words. In other words, the product of the square of a binomial in the form of a plus b squared or a minus b squared is always the square of the first term. So let's look at that. Let's break that down. So in other words, you shouldn't have to take it down to 5x minus 3 times 5x minus 3. If you understand the special case, you can take this first term, that's what it's saying, always the square of the first term. So 5x squared. We'll just write that down so we can kind of visualize it, and then we'll do the math. And then you're going to plus, and in this case, I should probably say subtract, because notice it's a difference. You're going to subtract twice the product of the first term and last term. So twice the product of 5x times 3. And then that last one, so we have this part done, and then plus the square of the last term. So that last term is 3, and then you square that, and you get your answer. So 5x times 5x would give you 25x squared. 2 times 5x times 3, well, 2 times 5 is 10, times 3 is 30, so negative 30x. And then 3 squared is 9. So again, it's a square of a binomial. I notice that as quickly I can do these steps. Now, if you're thinking, hey, Ms. Stell, that is way too much more work, I would rather just multiply like I learned in the last lesson, that is more than welcome to do that. If you notice this pattern, it may or may not make it more efficient. Again, we're doing a square of a binomial. I'll do another one example. So we have 4x plus 10 squared. So if we go through our steps, we're going to take the first term and square it. So 4x and squared plus, because it's the sum, 2 times the first term times the second term, or the last term. And then we're going to add the last term squared. So 4x times 4x is 16x squared plus 2 times 4 is 8 times 10 is 80x plus 10 squared is 100. So to me, once you know that pattern and you get used to it, that special case really does make it more efficient for me. Then I don't have to take so long to solve them. The second, or the last case we're going to look at, is called a difference of two squares. So this time it looks like a plus b times a minus b. They're the exact same values of a and b, except for one of them will be a positive and one of them will be a negative. Unlike the first case, they were both either positive or they're both either negative. This has a difference in one and a sum in the other. So how to look at the pattern here, or the shortcut or the efficient way, I'll show you with distributive. So we're going to take a plus b times a minus b. Again, this is called the difference of two squares. I'm more worried that you can just recognize them and know the pattern and how to solve. So if we do this, we're going to take this first a, we're going to multiply or distribute it to that second. So this would be a times a minus b. And then we're going to take that second b and distribute it to that second binomial. So plus b times a minus b. And then I'll go ahead and do the math. So a times a is a squared. A times negative b is negative ab. B times a is a positive ab. And b times a negative b is a negative b squared. Again, I always put them in alphabetical order because that way then I can see that they are the same term. If you turn around and call it BA and one AB, they are technically the same term. So I always keep it in alphabetical order to keep confusion. Now, if you notice, again, multiplying two binomials would have gave you this 4-term polynomial, which we know goes down into a trinomial, but these two middle terms are going to cancel each other out because one's positive, one's negative. So technically, you only end up with a squared minus b squared. Okay, let's look at that with the area model for my visual learners. So make a quick table here. Sorry, it's sloppy. We get a and a positive b here. We get a and a negative b here. So a times a is a squared. A times negative b is negative ab. A times b is ab. And negative b times a positive b is a negative b squared. Again, we have our a squared. We have our negative b squared. And we're going to notice that the negative AB and the positive B will be the same value, so it cancels each other out. So you only end up, if you recognize this, as a difference of two squares with a first term squared, the last term squared. Notice this is called a difference of two squares. That's because the answer always at the end is negative. Or in other words, I should say a difference. So it's the first term squared minus the second term or last term squared. And your example for that is going to be 2x minus 7 times 2x plus 7. Again, one is a difference, one is a sum when this works. This is different than that first one because it's one of each. So in other words, the product of a sum, in this case, and a difference of this case, of two binomials in the form of a plus b times a minus b, and I just flip those around so you can notice it doesn't matter which order they come in, is always the square of the first term minus the square of the last term. In other words, a squared minus b squared. This one I think saves a lot of time if you recognize it. So if you recognize this as a difference of two squares, you can take 2x times 2x, which would give us 4x squared. No middle term because they'll end up canceling each other out. I just proved that in the previous screen. And then it's going to be always a difference, and then 7 times 7, which is 49. And that to me is a lot quicker of solving. If we just want to throw one more up there, so we can have like 3x plus 5 times 3x minus 5. So again, if you recognize them, have to be one positive, one negative. You're going to take the first term, you're going to square it. In other words, 3x times 3x is 9x squared, and you go minus because it's a difference, and then 5 times 5 is 25. So to me, that saves a lot of time. Have a wonderful rest of your day, and hopefully you understand at least 2 of the special cases I taught you here in Algebra 1.